Thank you for the introduction. Good morning, ladies and gentlemen. Welcome to my presentation. I hope you enjoy it. It's entitled The Use of Big Data Analytics and Accident Learnings to Predict Heightened Railroad Risk. I would like to begin with a focus of the paper. So, firstly, I want to talk about what is big data and why it's useful. Then I want to go on to describe a data taxonomy that we've established for the railway. So we've looked at all the different types of data that are available or should be available. I then go on to talk about accidents and how they relate to the causes and the hazards. We've looked at 3 accidents which I will present. What we then do is, by using these accidents, we link the causes of the accidents to the data that may have been available that would have helped to predict the heightened risk that was in existence at that time, which led to the accident. Then what we did was we looked at, in the paper, we looked at what we might call the BD-ness of the data that was available, and we've categorized it using a system we've developed, which I'll explain. And then we'll show you a new approach that we're developing called the elbow tie. I'll then look at what the opportunities and hurdles are for this type of approach, and then I'll draw it all together with some conclusions. Okay, big data, a new dawn, hype. We hear a lot about big data. I was reading the other day that in the last 2 years, I think this was an IBM report, in the last 2 years, 90% of the data that's ever been produced by mankind has been generated in the last 2 years. So you can imagine that's a massive growth. But we also have this Internet of Things idea where we've got interconnected intelligent assets. And this can apply equally to domestic products or to the railway. For example, we can put sensors on our assets. We can put strain gauges. We can put accelerometers. We can put thermocouples on things, which will help us predict the condition of the asset. And as you can imagine, this if we cover the railway with these intelligent assets, then the amount of data generated will be tremendous, and we need a way to look at it. I saw this quoted the other day. This is a zettabyte. So this isn't a megabyte or a gigabyte or a terabyte. This is 1 byte to the power 27. It's a massive number, and these are the numbers we're talking. I like this graph from Gartner, which describes the uptake of new technology. So we have a technology trigger, then we've got this hype factor where we have elevated expectations, and then when they're not met, we have this trough of disillusionment. But then if the technology's got some value, then it will eventually climb up the slope of enlightenment, and eventually we will get something useful out of it. And with these technologies, we are approaching this plateau of productivity. These things are happening, and it's changing the way we do business. Okay, big data. Big data has been categorized or described using the 5 V's. So if something's big data, then it's likely to satisfy all these 5 V's. If it doesn't, then it may not be big data. If it satisfies 1 or 2, it just may be business as usual. So what we got? We got velocity. That's how fast the data approaches. Is it real time? Is it streaming? Volume. How much of it is there? How much do we have to deal with? Is it very high volume? Variety. How many diverse data sources do we have to contend with and to analyze? Veracity. That's how good is the quality of the data. And finally, we have value. How much value can be generated from the data? Can it help make things safer? Can it help save money? Can it help to avoid wastage? So it's something, if a data project satisfies all these 5 V's, then it is big data. That's what we would call big data. It's got all these 5 V's in heaps. What we did next was we established a data taxonomy for the railway. So we sat down and we thought about all the data that's available. So this could be structured data, such as condition monitoring data, or it could be unstructured data like incident reports or hazard logs, for instance. The structured data is much easier to analyse. The unstructured data, where you're dealing with real languages, that's much more problematic. Well, let's just have a quick look through this. So we've got we've got condition monitoring, we've got close calls, CCTV, asset data, maintenance, inspection data, design data. There could be weaknesses in the design. Finance data, quality management, safety management data, business risk data. This is all unstructured. Operational data, manning levels, data reports, spreadsheets, timetables, operational risk assessments. Then we've got social media, which could indicate a risk. Twitter, Facebook, all these things. Got external data, maps, environmental data. Then we've got personal data for people, health records, location history, education. Now, some of these data sources are probably more critical than others, but nonetheless, they would help build a picture up of what the risk levels are if you could look at them all together. So accident causation, this is some work done by M. Neal at the IMechE, and he looked at 43 different accidents in different industries, and he'd come up with these 14 different causes, and every accident he looked at had more than one cause. So we're looking at multiple complex causes, and you can see in this table that some of the most of the labels in it map across to that data taxonomy. For instance, training, weather, quality, design defects. So you can see there's a map in there. At the bottom of the page, we've got some of the rail accidents he looked at. I'm not going to go into detail on these, but we're going to cover Hatfield in a minute. King's Cross, that was a terrible fire in London that killed over 90 people, caused by a build-up of waste under an old wooden escalator. Clapham, that was a wrong side failure caused by maintenance error where they didn't terminate a wire correctly, so it touched another wire and put a signal to green when it should be red. Southall, that was caused by a passenger train hitting a freight train when the ATP was turned off. Ladbroke Grove, that was caused by a rookie driver passing through a red signal, thinking it was a yellow signal, and cancelling the warning and hitting a passenger train. Hatfield, we'll come on to. Potter's Bar was caused by maintenance errors where a set of facing points came loose and led to a derailment and 11 people killed. But you can see we've got this complex causation. Right, the 3 accidents we looked at were, the first of the 3 accidents we looked at was Santiago de Compostela. 91 people killed. Awful accident. I'm not showing this gratuitously. I'm showing it because, in a way, to remind us why we're doing what we do. So what was at play there? Well, there was no speed control transition. It was total reliance on the driver. The driver was distracted. There were train stability issues, or potentially train stability issues. Passenger survivability was an issue, a design issue. What we've done in our paper is linked these causes to potential data sources. We looked at Hatfield. This was in 2001, and this was where the track disintegrated on a curve. 4 people killed. Gauge corner cracking. This is where you get a subsurface crack, which doesn't go very quickly until it gets to a critical size, and then it grows much more quickly. And the way to control these cracks is by rail grinding. So the problem is that the railway had been privatised, and Railtrack saw themselves more as a management company than an engineering company, and they lost control of the situation shortly after they went out of business. The network had a nervous breakdown, and speed controls were put on everywhere. And what happened was there was a massive surge in accident fatalities on the road because people stopped using the trains because of the speeds were so low. So the accident we're going to look at in slightly more detail is this one in Spain, Castelldefels, which is near Barcelona. But this is the station involved. So there was a new underpass built. But what happened, this was in 2011, 12 people were killed, 12 kids who were going to a festival on the beach next door to the station. They got off the train was 10 minutes late, and they crossed the track and were hit by an oncoming express train. So what we do, if you look at this table here, we've linked the causes that we've derived to potential data. So the crowding on the platform, high spirits, subsequent trespassing. Well, CCTV would have revealed this. Also GPS data, social media, station design. Members of the public claim that it was not clear where the exit was. Well, that could have been revealed by close calls or station design. Timetable data. Well, the train was running 10 minutes late. The police were present, so emergency information could have been available. It was also supposedly a known problem, and this could have been tracked with GPS or close calls from driver. I think the point is that if you look at that station, if you'd been there a few minutes beforehand and you'd seen this train come in late, these kids roaming around, this high-speed train approaching, you would have been very worried. And our big data approach is the sort of tool that will be able to flag this up. What we did then is we looked at the BD-ness, or the BD quotient of each of those accidents. So we came up with a quotient of 67 for this Pleasure de Castelldefels accident. The other two, we came up with a quotient of 33% each. And I think what this says is that if it's a complex accident with lots of different media, then it will have a high BD-ness. The one like Hatfield is more or less business as usual. It's condition monitoring, it's good management. So you can see you've got a continuum of business as usual down to big data analysis. And this is down at this end, probably makes it more difficult. So what tool have we come up with? We come up with the bow tie. Why have we used this? Because there are plenty of other accident causation models. You've got the Swiss cheese that we looked at yesterday. We've got the something called STAMP that Nancy Leveson at MIT has come up with. We came up with this the bow tie. We came up with a bow tie because it's easy to understand and it's widely used. So let's just look at the bow tie. So in the middle we have a hazard. On the left we have causes which lead to the hazard, and on the right we have how the hazard propagates through to being an accident. And on the left we have the potential for avoidance, i.e. we can stop the cause becoming a hazard. And on the right we have mitigation, i.e. we can stop the hazard mitigating to a accident. So the idea behind this is that we link the data sources to these potential mitigations so that we can stop the cause becoming a hazard or the hazard becoming an accident. So what we're trying to do is flag heightened risk. So on the left of this diagram, we've got all these disparate data sources, and machine learning is a black art, and there's different camps. There's people who use Bayesian approaches. There's evolutionists who use genetic algorithms. You've got connectivists who use neural networks, and then you've got other ways of doing it. So it's a black art. And the main test is how well can it make inferences from data? How accurate is it? Now each one of these data sources in and of itself is useful. So a lot of these data sources already are go, no go, for instance. Derailment quotients, derailment forces, they're either too high or they're too low. What was talked about yesterday with level crossings, there's either someone in the crossing or not. Some of them are not quite so simple. Some of them just indicate that there's a heightened risk potential. But the main issue is that you've got this complex relationship between the data. And what we need is a system that can learn what bad looks like and one that knows what normal is. And that will enable it to red flag these heightened risk situations. Now, there's a lot of work to be done, obviously, but what we want to do is slowly build up our data sources so that eventually we have this all-seeing eye based on the knowledge generated by the data and the opportunity to visualize when we have heightened risk. So this elbow tie model, we're just designing the front end at the moment. So what you can do is you can drag and drop a workbook into here, which will automatically generate a bow tie, providing you structure the workbook properly. So this is an example of some work we've been doing recently on a derailment where a set of points, a stretcher bar and a set of points broke. So these are some of the causations. So what were the data sources? Maintenance, inspection records, train movements. So that's what we're trying to build up at the moment. An example of one of our data sources is some work I'm doing to predict derailment quotients using neural networks. Now this is interesting. We published a paper in 1999 on this, where we used a MATLAB to generate a neural network running on a Pentium processor, where we used a simulation package called Vampire to train a neural network, the relationship between the horizontal and vertical displacement of the rail and the lateral and vertical forces on the rail. So we then showed it some track data that it had not seen before, and then it inferred what the forces would be and predicted a derailment quotient. Now, as you can imagine, well, the vertical forces were quite easy to predict. The lateral forces were much more difficult because of the friction and the non-linear relationship. So we're doing a project now using this open source Google TensorFlow, and what we're going to do is do exactly the same work. What we're doing is using exactly the same work using much more powerful computing and this much more sophisticated deep learning algorithm. So hopefully it will be able to predict much more accurately the relationship between the track displacement and the wheel rail interface forces. So that's an example. So where's this going? Well, I actually see a lot of opportunities at the moment for safety. The first thing is that I see Chris mentioned yesterday safety 2, and this is the idea that we look at safety in a different way. Safety 1, the way we do safety now, is okay for simpler systems, but it was based on quite simple electromechanical systems where things like fault tree analysis, FMEA work quite well for component failures. But now we've got these complex socio-technological systems where we've got software, very difficult to understand systems where the operator probably doesn't understand fully how it works. Things like ERTMS and PTC are examples. So instead of looking at the failures, we look at how the system actually works and how it works in practice and not as imagined by the designer. And we build in a resilient system that can react to variations in the environment. So we look at how it works. We focus more on success than on failure. The second thing I see in this virtual circle is big data. We actually do analysis based on real data, not just expert opinion. We've got the data, let's use it. In the UK, we've got an initiative called Digital Railway where we're interconnecting the disparate parts of the railway using ERTMS and a traffic management system. But this will give the opportunity for people to share data much more easily. It will provide a backbone. And finally, all this information will enable us to simulate how the system works before we build it so that we can train people properly. And that sort of completes a circle. It allows us to take this safety 2 approach. The next thing that interests me is how this machine learning may affect how we do safety engineering. This is a copy of the life cycle. I think Jean-Marie showed us this yesterday, the V life cycle. Now it's interesting that every life cycle there are these activities that are recommended. If you look through the whole life cycle, these activities are all based upon data and logic. So this type of work could be right for automating. You could actually replace me maybe in 10 years with an algorithm. I won't care because I'll be retired. But I think that's an interesting story, how that will pan out and how safety will be done in the future. Now, all this won't happen without a few hurdles. I think these are just some of them. How do you get people to share data? People don't want to share data. Data is treated with confidentiality. So what can we do? Liability. Well, imagine that you've got data generated from an asset that indicates something's dangerous and you don't act upon it. That probably makes you liable. So that will need to be looked at from a legal standpoint and from a licensing standpoint. Also, if you put systems like this in place, if there's a lot of false alarms, then it will cause a lack of confidence in the system. I noticed on the motorway the other day, I was going to the airport and there was one of these signs saying animals on the line, on the road, and everybody slowed down. There weren't any animals. Next time you see it, you probably won't slow down. There might be some animals. Building a model is going to be a massive job. We're trying to get the project funded within the Data Science Institute at Lancaster University, but there's a lot of work to be done. And finally, how does one get safety approval for an algorithm like this? Because you can't look inside a neural network and see how it works because it writes its own software. the way we do software safety now, we use quite simple systems, and people can examine them, but you won't be able to do that with this. So that's going to be a major hurdle. Okay, to conclude. Well, we looked at the BD-ness of 3 accidents, and we saw that the more complicated, the more disparate the data was, the higher the BD rating that we came up with was. And the ones with lower BD ratings are probably what you might call business as usual, because it's condition monitoring, that type of thing. Maybe big data, but the ones with the higher rating, definitely big data. Another interesting thing is that intelligent algorithms are going to change how we do our work. As I explained, I mean, the blue collar people have already had robotics take away a few of the jobs and automation, but this is going to be a white collar phenomenon in the future, and it will include safety management, and it will include the way we work. So that's something we have to keep our eye on. The point is, this isn't going to stop. The genie's out of the bottle now. We can't stop this, so we have to work with it. That's a genie, by the way. But the real opportunity here is that once we get these models set up, they get better and better every year. As we get more and more data, they learn and they make better inferences. And one of the problems we've had in the past in the railways is that we haven't always learnt from experience, and we keep repeating mistakes. If you have these systems in place, that is very unlikely to happen. That's our website. Anyway, thanks for listening, and I appreciate any questions coming on time there. Thanks.